like that.
Testing. Testing. Are reasonably loud? You'll know it's not fake. Okay? Good. Well, first of all, I am deeply honored to be the stand-in for Julian Schwinger. To say the least, I feel inadequate about this, except I do know Julian. I've come to know him, shall I say. I didn't know him at all, except my first meeting with him briefly at the first annual conference on cold fusion in Salt Lake City, where I heard him speak. And the next time I heard from Julian Schwinger was when my publisher sent me a letter, I think it must have been in April of 1991. He had been sent a copy of the galleys of Fire from Ice. It was about to be published, and I was about to fly away from MIT. And I was stunned when I received a marvelous letter, part of which is quoted on the cover of Fire from Ice. And I guess since I'm doing this video, I can't resist. Let's hear this. Oh, come on, there has to be an advertisement. Eugene Mallon has produced a sorely needed, accessible overview of the cold fusion model. By sweeping away stubbornly held preconceptions, he bears the truth implicit in a provocative variety of experiments. Unfortunately, Julian has been outvoted by many other Nobel laureates who've signed their names to the infamous Cows book. But I'm happy about that because it doesn't bother me at all, as Douglas Marson knows and objects to. I have established a flypaper list. I call the Tom's book a flypaper catcher, whereby all those who praise it will be caught on a flypaper and trashed for it. All right, Julian wouldn't. Well, Julian actually said I could do whatever I wanted. I could introduce commentary. So I assure you, even though I'm a little under the influence of alcohol and deuterium, I have permission to do this. But I'm not. I also assure you, I have not changed Julian's theory. I have not changed Julian's theory, and I have not introduced any equations which he did not put down. They're very simple, you all understand. Okay, well, the title of Julian's talk is A Brief History of Mind, which I think is poetry. At least it rhymes. And by the way, afterwards, if you wish, or tomorrow or whatever, if you want a copy of this, and there are a lot of spelling errors, unfortunately, including misspelling Fleischman's name, I will provide you with a copy. Okay. I can't really reproduce Schwinger, but I was right. As Polonius might have said, neither a true believer nor a disbeliever be. From the very beginning, in a radio broadcast on the evening of March 23, 1989, I have asked myself whether Pons and Fleischmann are right, but whether a mechanism can be identified that will produce nuclear energy by manipulations at the atomic, the chemical level. Of course, the acceptance of that interpretation of their data is needed as a working hypothesis in order to have quantitative tests of proposed mechanisms. As a longtime nuclear physicist, the knee-jerk reaction to the idea of a DD reaction without significant neutron production brought in words like helium-4 and the Mossbauer effect. I tried without success to contact Pons and Fleischmann to the point of sending a letter to the Los Angeles Times, which was garbled in the editing process. Finally, with the help of a friend, contact was made in the early part of April, and I went to Salt Lake City. This is April 1999. There, I was assured that they knew about helium-4 and were shown a peak in a spectroscopic readout, which I was told was helium-4. Soon after my return to Los Angeles, references to helium-4 disappeared, to resurface only relatively recently. I do not have to, but shall remind you of the two fundamental problems that the acceptance of Pons and Fleischmann's excess heat as nuclear in origin entails. Number one, what accounts for the absence of particles that are familiar in ordinary hot fusion, such as neutrons of DD going to a neutron plus helium-3, and the high energy gamma ray of DD going to gamma plus helium-4. Very early in my thinking, I added the conventional reaction P plus D goes to gamma plus helium-3. Why? Mostly because it would also be there. One cannot produce heavy water without some contamination of light water. Hot fusion relies on number two. Hot fusion relies on achieving enough kinetic energy to overcome the Coulomb repulsion between light charges. How then can cold fusion, operating far below these levels, ever achieve fusion? Incidentally, I have read and heard that my solution to the Coulomb barrier is to forget it. Not even an absent-minded professor, which I am not, would go that far. Critics should learn to operate within the bounds of sanity. Douglas? My first attempt at publication, for the record, was a total disaster. Quote, this is the title, quote, Cold Fusion, a Hypothesis, was written to suggest several critical experiments, which is the function of hypothesis. The masked reviewers to a person ignored that and complained that I had not proved the underlying assumptions. Has the knowledge that physics is an experimental science been totally lost? Yes. That was my remark. The paper was submitted in August 1989 to Physical Review Letters. I anticipated that PRL would have some difficulty with what had become a very controversial subject, but I felt an obligation to give them the first chance. What I had not expected, as I wrote in my subsequent letter of resignation from the American Physical Society, was contempt. Hypothesis, the article, was eventually published after protracted delays in a 1990 issue of a German periodical. And, by the way, I have a list of all Schwinger's cold fusion and other references related to this talk, which I can give you after or get a copy. Doesn't have any significance in 1993. I cite the following excerpts. Quote, this cold fusion process of Pons and Fleischmann is not powered by a DD reaction. Rather, it is an HD reaction, which feeds on a small contamination of D2O by H2O. The HD reaction, P plus D, I guess I still have it here. He's just reciting it again. P plus D goes to helium-3 does not, plus a neutron, does not have an accompanying gamma ray. The excess energy is taken up by the metallic lattice of PD alloy with D. And finally, quote, concerning the oft-repeated demand for a control experiment using H2O, one should note the possibility of a converse effect of the HD reaction. Through the natural presence of D2O in ordinary water, such control experiments might produce an otherwise puzzling amount of heat. A following paper entitled Nuclear Energy in an Atomic Lattice, Part 1, was sent directly to another German periodical in November of 1989. As of today, the only memorable part is a quotation from Joseph Priestley. In this business, more is owed to what we call chance, that is, to the observation of events arising from unknown causes, than to any preconceived theory. The editor thought it necessary to add a total disclaimer of responsibility, ending with, "We leave the final judgment to our readers," which I did put into Fire from Iceland. I thought that was very amazing. In my naivete, you spell that one too, I had thought that was always so. When part 2 of this nuclear energy and atomic lattice paper was submitted, it was simply rejected. The fix was in. I gave a talk with the same title, Nuclear Energy and Atomic Lattice, at Salt Lake City in March of 1990. The HD hypothesis of the dominance of the PD reaction has the pragmatic advantage of suppressing neutron production at the level of excess heat generation. But to quote from that lecture, quote, "A well-trained hot fusioneer will instantly object that there must also be a 5.5 MeV gamma ray. He will not fail to point out that no such radiation has been observed. Indeed." Quote, again from the article, "But consider the circumstances of cold fusion. At very low energies of relative motion, the proton and deuteron of the HD reaction are in an S state, one of zero orbital angular momentum, and therefore of positive orbital parity. The intrinsic parities of proton, deuteron, and helium-3 are also positive. Then, the usual dominant electric dipole radiation, which requires a parity change, is forbidden." End of quote. I turn from missing, in quote, radiation to Coulomb repulsion, end quote. Treatments of nuclear fusion between positively charged particles usually represent the reaction rate as the product of two factors. The first factor is a barrier penetration probability. It refers entirely to the electric forces of repulsion. The second factor is an intrinsic nuclear reaction rate. It refers entirely to nuclear forces. This representation may be true enough under the circumstances of hot fusion. But in very low energy cold fusion, one deals essentially with a single state or wave function, all parts of which are coherent. It is not possible to totally isolate the effect of the electric forces from that of the nuclear forces. The correct treatment of cold fusion will be free of the collision-dominated mentality of the hot fusioneers. We haven't even gotten to the punchline. To speak of transferring energy to the lattice is to invoke lattice excitations or phonons. At about the time of the Salt Lake City meeting, or shortly after, I became dissatisfied with my treatment and began to reconstruct phonon theory. A note entitled Phonon Representations was submitted to the Proceedings of the National Academy of Sciences in June of 1990. The abstract reads, quote, "The gap between the non-localized lattice phonon description and the localized Einstein oscillator treatment is filled by transforming the phonon Hamiltonian back to particle variables. The particle coordinate, normalized wave function for the phonon vacuum state is exhibited." A month later, I submitted a second note with the title Phonon Dynamics. And by the way, in case any of you may be confused by this, If you're if you're a member of the National Academy of Sciences, you get instantly published in the proceedings. There's no peer review or anything. You're just there, okay? So he's not contradicting himself about peer review. So the title Phonon Dynamics abstract reads, an atomic lattice in its ground state is excited by the rapid displacement and release of an atomic constituent. The time dependence of the energy transfer to other constituents is studied. End of quote. The third and last note is called Phonon-Green's function. Its abstract is, quote, the concepts of source and quantum action principle are used to produce the Phonon-Green's function appropriate for an initial phonon vacuum state. An application to the Mossbauer effect is presented. End of quote. I remind you that the Mossbauer effect refers to an excited nucleus of an atom embedded in a lattice that decays with the emission of a gamma ray, thereby transferring momentum to the lattice. There is a certain probability that the phonon spectrum of the lattice will remain unexcited, as evidenced by the absence of the gamma ray energy of the redshift associated with recoil energy. A casual explanation of the Mossbauer effect has it that the recoil momentum is transferred to the lattice as a whole, so that the recoil energy, varying inversely with the mass of the entire lattice, is extravagantly small. As Pauli would say, and boy did I love that other Pauli statement about semiconductors, so this is great. As Pauli would say, even to God, das ist falsch. Practicing my German class. Das ist falsch. All right. Julian had to actually explain that anecdote to me, since Pauli was known to be the kind of guy who would dispute with God as to how he constructed the universe, so that's why it's funny. Okay? In case you didn't know. The spontaneous decay of a single excited atom in the lattice is a localized event, the consequences of which flow at finite speed out into three-dimensional space, weakening as they travel. This is the microscopic event with no dependence on macroscopic parameters such as the total mass of the lattice. Unmentioned in the abstract, but of far greater importance, is another situation. To quote, what happens if the momentum impulse is applied not to one, but to all lattice sites? End of quote. The reader is invited to, quote, recall that the lattice geometry is not absolute, but relative to the position of the center of mass of the entire system. Thus, the injected energy can be read as the kinetic energy transferred to the lattice as a whole. More about this shortly. In the last month of 1990, I went to Tokyo. The occasion was the 100th anniversary of the birth of a famous Japanese physicist, perhaps most familiar for his part in the Klein-Nishima formula for Compton scattering. On a day that, to my surprise, I found uncomfortably close to another infamous day, I delivered a lecture on cold fusion, does it have a future? And that infamous day is about now. The abstract reads, quote, the case against the reality of cold fusion is outlined. It is based on preconceptions inherited from experience with hot fusion. That cold fusion refers to a different regime is emphasized. The new regime is characterized by intermittency in the production of excess heat, tritium, and neutrons. A scenario is sketched based on the hypothesis that small segments of the lattice can absorb release nuclear energy. I pick up the last sentence of the abstract with this quotation from the text. Quote, if the gamma rays demanded by the hot fusioneers are greatly suppressed, what agency does carry off the excess energy in the various reactions? One must look for something that is characteristic of cold fusion, something that does not exist in the plasma regime of hot fusion. The obvious answer is the lattice in which the deuterium is confined. Imagine then that a small but macroscopic piece of the lattice absorbs the excess energy of the HD or DD reaction. I advance the idea of the lattice playing a vital role as a hypothesis. Intermittency is the hallmark of cold fusion. Does the lattice hypothesis have a natural explanation for intermittency? A close approach to saturation loading is required for effective fusion to take place. But surely, the loading of deuterium into the palladium lattice does not occur with perfect spatial uniformity. There are fluctuations. It may happen that a microscopically large, if macroscopically small, region attains a state of such lattice uniformity that it can function collectively in absorbing the excess nuclear energy that is released in an act of fusion. And that energy can initiate a chain reaction as the vibrations of the excited ions bring them into closer proximity. So begins a burst. In the course of time, the increased number of vacancies in the lattice will bring about a shutdown of the burst. The startup of the next burst is an independent affair. This picture is not inconsistent with the observation of extensive cracking after long runs. What answer did I give just 3 years ago to, does cold fusion have a future? I said, quote, did I write this down? Yeah, I think I did. It's pretty important. I had little hope for it in Europe and the United States, the West. It is to the East, and specifically to Japan, that I turn. Inspired by good soba and sushi, I dashed off a short addendum that Progress of Theoretical Physics received in January and published in April of '91. The abstract of nuclear energy in atomic lattice causal order is: the extremely small penetrability of the Coulomb barrier is generally adduced to dismiss the possibility of low-energy cold fusion. The existence of other mechanisms that could invalidate this logic is pointed out. Here are excerpts. Quote, implicit in this line of thought of negligible penetrability is the apparently self-evident causality assignment that has the release into the surrounding environment of energy at the nuclear level occur after the penetration of the Coulomb barrier. One would hardly question that time sequence when the environment is the vacuum, but does it necessarily apply to the surrounding ionic lattice? Another reading is possible, one in which the causal order is reversed. Why? Because in contrast with the vacuum, the lattice is a dynamical system capable of storing and exchanging energy. The initial stage of the new mechanism can be described as an energy fluctuation. With the uniform lattice segment, that takes energy at the nuclear level from a PD or DD pair and transfers it to the rest of the lattice, leaving the pair in a virtual state of negative energy. For the final stage, consider the PD example where there is a stable bound state, helium-3. If the energy of the virtual state nearly coincides with that of helium-3, a resonant situation exists, leading to amplification rather than the Coulomb barrier suppression. It would seem that two mechanisms are available, but are they not extreme examples of mechanisms that in general possess no particular causal order? The last lecture on cold fusion was delivered twice in the fall of 1991 to celebrate the birthdays of former students, one of whom is at MIT, a hotbed of hot fusioneers, at least for now. They won't be around for long. The cover title, A Progress Report, injects a bit of my own nostalgia. Not long after the simultaneous arrival of myself at Berkeley in World War II, Robert Oppenheimer gave a lecture with that title. As he explained, it meant only that time had elapsed. That also applied to the first part of my birthday lectures, energy transfer and cold fusion, with one exception. This is what he said. Quote, I note here that the interesting possibility that helium-3 produced in the PD fusion reaction may undergo a secondary reaction with another deuteron of the lattice. I don't know if I have that here. I think I may be able to just eliminate it. Let me just understand it from the text. I note here that helium-3 produced in the PD fusion reaction may undergo a secondary reaction with another deuteron of the lattice, yielding lithium-5. An excited state of lithium-5 lies close by, parentheses. The latter is unstable against disintegration into a proton and helium-4. Thus, protons are not consumed in the overall reaction, which generates helium-4. To this, I add, as of sometime in 1992, that observations of helium-4 with insufficient numbers to account for total heat generated are consistent with the preceding suggestion. The initial PD reaction produces heat, but no helium-4. The secondary reaction generates heat and helium-4. There is more total heat than can be accounted for by helium-4 production. The smaller the ratio of secondary to primary reactions, the more the helium-4 production will be incapable of accounting for the heat generation. A second part of a progress report is entitled Energy Transport in Sonoluminescence. What is that? The text begins with, quote, the suggestion that nuclear energy could be transferred to an atomic lattice is usually dismissed because of the great disparity between atomic and nuclear energy scales of the order of 10 to the 7th, say. It is therefore of great psychological importance that one can point to a phenomenon in which the transfer of energy between different scales involves an amplification of about 11 orders of magnitude. It all began, quote, he's quoting from his paper given at MIT and the University of Pennsylvania. Quote, it all began with the sea trials in 1894 of the destroyer HMS Daring. The onset at high speed of severe propeller vibrations led to the suggestion that bubbles were forming and collapsing, the phenomenon of cavitation. Some 23 years later, during World War I, Lord Rayleigh, no less, was brought in to study the problem. He agreed that cavitation, with its accompanying production of pressure, turbulence, and heat, was the culprit. And, of course, he devised a theory of cavitation. But there he seems to have fallen into the same error as Isaac Newton, who, in his theory of sound, assumed isothermal conditions. As Laplace pointed out in 1816, under circumstances of rapid change, adiabatic conditions are more appropriate. During World War I, the growing need to detect enemy submarines led to the development of what was then called, by the British anyway, subaqueous sound ranging. The consequent improvement in strong acoustic sources found no scientific applications until 1927. It was then discovered that when a high-intensity sound field produced cavitation in water, hydrogen peroxide was formed. Some 5 years later came a conjecture that, if cavitation could produce such large chemical energies, it might also generate visible light. This was confirmed in 1934, thereby initiating the subject of sonoluminescence, SL. I should, however, qualify the initial discovery as that of incoherent SL, for, as cavitation noise attests, bubbles are randomly and uncontrollably created and destroyed. The first hint of coherent sonoluminescence occurred in 1970, when SL was observed within accompanying cavitation noise. This indicates that circumstances exist in which bubbles are stable, but not until 1990, funny year, was it demonstrated that an SL stream of light could be produced by a single stable cavity. Ordinarily, a cavity in liquid is unstable, but it can be stabilized by the alternating cycles of compression and expansion that an acoustic field produces, provided the sonic amplitudes and frequencies are properly chosen. The study of coherent SL, now underway at UCLA under the direction of Professor Seth Putterman, has yielded some remarkable results. What to the naked eye appears as a steady, dim blue light, a photomultiplier reveals to be a clock-like sequence of pulses in step with the sonic period, which is of the order of 10 to the minus 4th seconds. Each pulse contains about 10 to the 5th photons, which are emitted in less than 50 picoseconds. That is about 10 to the minus 11 seconds. When I first heard about coherent sonoluminescence, my sister, some months ago, in June 1991, my immediate reaction was, this is the dynamical Casimir effect. The static Casimir effect, as usually presented, is a short-range, non-classical, attractive force between parallel conducting plates situated in a vacuum. Related effects appear for other geometries and for dielectric bodies instead of conductors. The bubble in water is a hole in the dielectric medium. Under the influence of an oscillating acoustical field, the bubble expands and contracts with an intrinsic time scale that may be considerably shorter than that of the acoustic field. The accelerated motions of the dielectrical material creates a time-dependent, dynamical electromagnetic field, which is a source of radiation. Owing to the large fractional change in bubble dimensions that may occur, the relation between the field and source would be highly nonlinear, resulting in substantial frequency amplification. The mechanisms that have been suggested for cold fusion and sonoluminescence are quite different. So I wrote in 1991. But they both depend significantly on nonlinear effects. Put in that light, the failures of naive intuition are understandable. So ends my progress report. In the more than 2 years that have elapsed since the birthday lectures, the 1991 ones, I have concentrated on the theory of coherent sonoluminescence. Why? Because of the two physical processes that naive intuition rejects, it is coherent sonoluminescence that exists beyond doubt. And I have to add this commentary right here. Julian Schwinger is not big on looking at all the latest data. In fact, he doesn't want to hear about it much. Therefore, he doesn't know that cold fusion is proved already. Okay. But he hears from me periodically, and he gets a little bit of experimental results filtered in. Oh, and I forgot. Now comes the punchline. Let me give that sentence again, so you can have the punchline. In the more than 2 years that have elapsed since the birthday lectures, I have concentrated on the theory of coherent sonoluminescence. Why? Because of the two physical processes that naive intuition rejects, it is coherent sonoluminescence that exists beyond doubt. No, Mr. Taubes, not even you could cry a fraud. Too many people have seen the light. With the advantage of reproducible data under variable circumstances, constructing a convincing theory for coherent sonoluminescence should be by far the simpler. That, in turn, should supply analogies for theory construction in a domain that is characterized experimentally by, quote, irreproducibility and uncontrollable emissions and bursts. My gut feeling about the Casimir effect in a dynamical role first needed some brushing up in the static domain, which I had not thought about for 15 years. My progress in doing that, along with needed simplifications, is reported in 3 notes, each published in 1992. 2 of them share the title, Casimir Energy for Dielectrics. Each note acknowledges the stimulation provided by the phenomenon of coherent sonoluminescence. I give only this brief excerpt concerning the action quantity W sub 0. What the static and dynamic Casimir effects share in the reference to the quantum probability amplitude for the preservation of the photon vacuum state, exponential of I W sub 0, that the vacuum persistence probability is less than 1 in a dynamical situation where photons can be emitted is expressed by a non-zero imaginary part of W sub 0. In a static situation where W sub 0 is real, the shift in phase associated with a time lapse identifies capital E, the energy of the system. In the latter part of 1992 and in 1993, 5 papers were submitted under the cover titled Casimir Light. The individual ones are called successively the glimpse, the source, photon pairs, pieces of the action, and field pressure. The first 3 notes adopted the oversimplification, the bubble collapse, the source of radiant energy is instantaneous. Pieces of the action begins to remove the more egregious aspects of that treatment End of quote. The abstract reads, more realistic dynamics for the collapsing dielectric fluid are introduced in stages by adding contributions to the Lagrangian that forms the action. The elements are kinetic energy, Casimir potential energy, air pressure potential energy, and electromagnetic coupling to the moving dielectric. There are successful tests of partial collapse time and of minimum radius. This paper ends with a veiled question. If, as it would seem, a mechanism exists that transfers kinetic energy of a macroscopic body into energy of microscopic entities, could there not be, in different circumstances, a mechanism that transfers energy of microscopic entities into kinetic energy of a macroscopic body? Seems obvious, doesn't it? What in 1991 seemed to be only a pairing of two intuitively improbable phenomena, quote, the mechanisms that have been suggested for cold fusion and sonoluminescence are quite different, end of quote, now emerges as related ways of transferring energy between macroscopic and microscopic objects. The paper Casimir Light Field Pressure begins with a question. How does a macroscopic classical hydromechanical system driven by a macroscopic acoustical force generate an astonishingly short time scale and an accompanying high electromagnetic frequency, one that is at the atomic level? In response, I offer the hypothesis that light plays a fundamental role in the mechanism. Provocatively put, the collapse of the cavity is slowed abruptly by the pressure of light that is created by the abrupt slowing of the collapse. The hypothesis becomes more quantitative with this supplement. And he goes on. The conditions for light emission are at hand when the fluid kinetic energy becomes independent of t, time, for a short time interval, and that similar remarks apply immediately after the emission act. In effect, one is picking out the circumstances for spontaneous radiation from a coherent state of definite energy to another such state of definite lower energy. The equation of motion, along with the conservation laws, that is supplied by the action principle, leads to a picture of what happens during abrupt slowing. Just before that begins, there is no significant field. Then the field strength rises rapidly in the vacuum region, giving a positive value to the outward pressure. The slowing has begun. That process will cease when the field, slowing at the speed of light toward the outer dielectric region, has produced the countering pressure. Quote, the somewhat mysterious initial hypothesis has emerged, clarified, as an unusual example of a familiar fact. Spontaneous emission of radiation by an electric system is a single indivisible act that obeys the laws of energy and momentum conservation. Now, finally, returning to the 1991 causal order note, with the example of the reaction, PD goes to helium-3 plus lattice energy, one also recognizes that this is a single, indivisible act. So ends this progress report. Julian Schwimmer. That's it. Well, I can't actually say that you can ask questions. But try. Since I've had a few bubblies, maybe I'll come up with some good answers. Yes, Mario.
I'd like to just make a few comments about Julian Schwimmer, things that I personally know, and then raise a question perhaps you can relate to them.
Sure.
Of the 3 Nobel laureates for the development of quantum electrodynamics, his development was the most mathematical and the most rigorous. There's no question about his credentials. Feynman, Tomananga, in an area that I did work in, I believe he was the best, most thorough treatment of synchrotron radiation. What's maybe not well known is that he probably was the first to conceive of unification of the electroweak theory, which he suggested to Sheldon Glashow to work on, and for which he gets little or no credit because he loved to credit the word. He also had the idea that possibly one of the big mysteries of how an electron holds together because the charge we're going to repel might be explained by the Casimir effect, which for plates gives you attraction, and assigned it to his graduate student Timothy Boyer. But unfortunately, perhaps because of marriage, it may really be a good one to this point as far as the analysis goes. They found a repulsive Casimir effect of the sphere rather than attractive, but I think it may still be attractive. So I'm one of the first to pay homage to Julian Schwinger and to feel that I'm an anti-comparison. Nevertheless, we all are human. I make mistakes. He has made mistakes which he's later corrected in other papers. And I just don't understand how maybe you can shed light, or we can through you shed light on what reversal of causality means and what it means to have heat preceding and exceeding the fusion product, the fusion force. Because at this stage, without further clarification, it sounds like mysticism. I don't know.
Right. He has elaborated on that, and I can't shed light on that. So I apologize for that. But if you read his papers, and as I say, I do have a list. You could look them up. Interestingly, you should comment about his role in winning the Nobel Prize with Feynman and Tomonaga. I find it, as a historian of this subject, somewhat amazing that many of the critics of cold fusion have shamelessly, should I say, referred to statements made by Dr. Feynman to the effect of the easiest person to fool is yourself. They picked that statement out as somehow applying to this. I've talked to Julian about this, and of course we will not know the answer unless we have the spirit of Feynman in the room as to whether he really would have attacked cold fusion the way mainline physics has attacked it. But Julian Schwinger has told me that he cannot imagine Feynman reacting the way the mainline physics community has reacted to this. Not to say that Feynman would believe cold fusion, but it is the opinion of Julian Schwinger that he would not have reacted this way. My own view, having just casually observed Feynman in his books and so forth, is that he would absolutely not do it. In fact, he would have a lot of fun. He'd probably be here at ICCF-4 playing the bongo drums. But there was another remark I was going to make in that context. Yes, in the book, I think it's surely you're joking, Mr. Feynman. I wish I had brought the text. Right after that part that Taubes and everyone else quotes, you're the easiest person to fool, you fool yourself. There's another statement after that, which I meant to give to Darth Vader. I mean, John Heisinger. And that is, if I can recall it, it's roughly, no scientist should fool the public. And I think, unfortunately, that's what's happened in this case. If fooling the public means asserting that we have the answer for sure, it's utter nonsense and garbage. Not that you have to believe it, but I think what's happened in the story is very early on, they said, it's obvious nonsense and garbage, goodbye, and they did indeed fool the public. End of my speech. Any other questions? Must be some questions. Dean?
I was thinking about his reaction, the P plus D reaction, and then you go to the lithium and it's recycled and you get another P back.
Lithium disintegrates immediately.
Right. The interesting thing about that is you have a certain number of P's sitting around and they're fused granular, and that determines what's going on. So the thought arises, has anybody looked at the possibility of running the liquid with varying ratios of light water to heavy water, rather than assuming that all heavy water is the same in the liquid proton?
Oh, yeah, well, that's Douglas Marcy who pointed that out, and the experiments have been. Hagelstein. Well, the ratio, did Hagelstein point those ratios out? Fritz, or
I'm sorry?
Peter Hagelstein pointed out those?
Peter Hagelstein pointed that out at the least as early as the common meeting.
Yeah. Incidentally, you know, the work by Dr. Srinivasan and others showing, and I think Dr. Montoya recently, showing fractions of heavy water added to light water shed some light on, not a full range of parameters, but at least some. And Dr. Bush, I think, also mentioned that he has used dedeuteраted water, cutting down from the usual level to 10,000 barrels. Yes, Bob.
The comment on reversible causality, in Bohm's book on quantum mechanics, if you refresh your memory, he says that resonant transparency seems to be a reversible causality because the naive view is how can what a particle is going to do after it has penetrated the potential barrier and entered some other place affect what it is going to do before it enters. But he says if you think about it as a wave instead of a particle, then it's not a reversible causality. It could be that.
By the way, did you use a resonance transparency as a term in the textbook?
No, I picked that up from you. I think it's a wonderful term. Wave it on the flag.
We coined that word.
Yes.
Well, any other questions? Does anyone have a question? Well, thank you very much. And one other quote that I think kind of goes along with this. You can find it in my book. I don't know what page. But quoting the Bible, the journalist Bob Bazell of NBC said to us in the 1990 first annual conference. He said it's a sure bet that cold fusion will bubble off into oblivion. It may bubble off.
The question of old age, right? You made a discussion remark. You made a
Yes.
the case of the molten salt electrolysis.
Leon.
Gases of water.
Well, helium-3 wouldn't go to helium-4, you just have helium-3. But the lithium-5 would go to...
Yeah, well, why in molten salts? Why don't you get the same molecules?
Well, no, I mean, my question was the data shows I know overall, I think that's very prolific.
Right? Absolutely.
So, Liz, my point was that Liz, possibly producing none, had a high overvoltage, 2 volts. So you couldn't generalize from the data chain to taking a low overvoltage, you wouldn't get high loading of high overvoltage. That's my point. That was the point I was trying to figure out.
Essentially, overvoltage proportional to the national activity. Right? So that's how those two are related.
Well, that's one source of overvoltage. That's one source of overvoltage. If you have a passivation layer,
Forget it. All of that will jump to be subtracted.
That's what you
well, that's just not what I
Yes, and they're around.
Just listen for a second. That's what the viscous
More than that.
I've talked to last week. I've noticed her I sent some letter and you can only notice that is proportional to the long and it was that is all the questions shown in the Without conversion, you can go into the phase higher, and then the pressure at the lower pressures, or activity at the higher pressures, because better goes into activities, because the coefficient starts
Is she ready to travel ride?
they know they have. What the loading is at various concentrations or activities. You can convert from those concentrations. And what you find is that those high temperature stuff for the same voltage as the low temperature. You get that's all. Yeah, that's all you say.
I have read his papers for many years. So I'm familiar with his work, and after I read one of his papers, I wrote him a letter. I wrote out an answer, so I don't know if he got the letter, didn't get the letter. And I tried calling the physics department, he said, oh, he's not there. I just thought, I'll check information. There was his instrument. So I called, she answered the phone, she said, that's the judge. So she said, he doesn't speak to Spanish. So I left a message, and she said she would ask him.
Now maybe that should be
Calls
called
her
over.
back, it was a long distance call.
Oh,
She is, I don't know what he does on it. Behind every successful man is a good one. I believe that. Yes, yes.
In that case,
For certain. Thank you.
Is the positive. Because the negative hydrogen ions go to the and form the connected hydride. Now, out of whatever voltage you have, and after he was talking about 2.1 volts, out of that, most of it, much of this is we can't say most.
I think almost none of those.
Because at his high, his electrolyte resistivity is also being fairly small. In the order of a fraction of an ohm centimeter. The voltage trust isn't all that high. So, but nevertheless, he loses some. He certainly loses some heat. The cell voltage is going to be applied voltage. And the residue flux, so that would be the over voltage that stays on the anode. My point is, I would say the activation of voltage, you really subtract the combination of voltage. And then you are left with a let's call that concentration. Okay? My point is that this is not all facts. This is no speculation, nothing I make up right here. It is that concentration that enters into the relationship that relates, and of course this is nothing else but E minus E squared. Where this is still a thermodynamic potential, whereas as you put this it's no longer a thermodynamic potential. And this is what we call then the concentration voltage. That refers to the surface. That's absolutely right, to that surface. And that is RT over NA. That's the number of electrons burning temperature gas times the log variable of the activity of the hydrogen directly on the surface over a reference voltage concentration in okay? That's very good. So what I'm saying is we now have a relationship typically you can have the concentration of the voltage, which incidentally, people determine like from Moscow and our school in Munich, and then you take that determine separately out of pulse experiments and determine the equivalence activity right in the surface. It is that activity determines the loading. Okay?
I know, I don't agree with that.
Oh,
Because the loading in the bulb, that determines the chemical potential of this one. The chemical potential is concerned with this chemical potential down here.
down here meaning at some distance from the electrode.
On the metal side of the diode.
You're absolutely right.
I mean, this, if you
That's your metal, that's the
here's your
electrode.
electrolyte.
All right. So what this is the activity and electrical constitution.
That's right here. Right there, right there.
What is this thing here?
That's a dielectric layer. Maybe an oxide layer.
Well, this oxide layer
Maybe.
is not established at all in these conditions.
Well, but you know, he didn't find for it.
If there is a resistant layer in front of us, then I say look indeed at the equilibrium between the hydrogen right here and the inside here, and then we have to look at how this activity relates to this one. It's a different activity. And then we have to modify the activity I'm talking about here by the presence of the resistance layer. A resistance layer that, by the way, has got to have
Right, right. That's what I would say. Yeah,
but
yeah.
I'm assuming that this is non-resistant.
I don't think that's true because
Okay, but I just said if there is one, it still doesn't change the essence of the resistance because then you simply consider that the activity here, that activity determines an activity right in this interface, that's activity as an interface determines what the concentration of atomic element is in the atoms of the palladium.
well, but it seems to me that you have a potential drop process. Basically, the electron and the ions on this surface have to go up to the concentration to get back to the solution. So,
Because it's important.
so you kind of fill this up until that reverse current goes into the forward current.
Well, no, I understand.
And that is much higher density than you would have. A drop, I mean, it starts off with a big old drop, but it gradually decreases until you have
Yeah, you would never have that 2-volt drop across this resistant layer. You just wouldn't. You have much of it, the total cell voltage of the cathode, you have the electrolyte, you have some of it across the resistive layer, and the rest of it you need as a driving voltage connection to change the interface.
But you have 3 different ones. You had 600 million, 300, 500. These balls, straight line.
Yeah.
That way to 0 volt, that's 2 volts. That to me is polarized layers. If you look at this pattern, there's people.
This here is the total voltage, cell voltage at 0 volts, which includes the difference in chemical potentials between the 2 metal phases. That's what you measure.
Well, this is 2 volts. Actually,
Most of it is the thermodynamic voltage.
No, the
difference of the
thermodynamic voltage.
electronegativity of the 2 electrons.
no, that's around 2/10 of a volt per glass. Very small for this particular glass. In fact, the thermodynamic voltage is exactly what this recording was. Japanese, the thermodynamic voltage plus the IR guns, they were running about 3/10 of a volt. And had these high currents. Or maybe 2/10 of a volt. That's the thermodynamic force drop IR drop across the electrolyte plus whatever is going on in the cathode. I run these things, they run, you know, that's voltage. But you can run these things and then a layer will form on the body layer, capacitation line, voltage will suddenly jump up like that.
How the voltage precisely splits up between the various phases is immaterial to the point I tried to make. The point I'm trying to make is that the driving voltage that determines what kind of stability you have here is the concentration of molecular hydrogen right at the interface. In your case,
It's right
this
here.
is true. Well, and I'm saying that relates to the concentration over voltage here, all right? And that is the driving force that determines the concentration of C. Now with that, you calculate activity. With that activity, you go into the phase diagram. And if you give them temperature, you know your operating phase. You get the
But the concentration is going to be higher here than here because they have this voltage drop. And you have to make you have that concentration ratio that makes this that activation ratio between activity level here compared to here. That ratio has to give you 2 volts.
Whatever the voltage drop is across this,
Right, whatever
2
the
volt or whatever it is, and that but simply feeds in the transfer equations, right? The driving forces, namely the concentration gradient as well as the field term, and thereby one can get for the given flux, which is determined by the current density, one gets the concentration. But the major point I'm making is the temperature that is looking at, the phase diagram tells you what the loading should be, and he gets values very close to that.
But I'm just saying that when you have a potential drop, and this concentration layer here is higher than it is here. That's what I'm saying. That's what I said. For the concentration layer here. But they're not appropriate for the concentration layer here.
I agree.
And this concentration layer here
Yes.
determines the concentration
But
of the
nobody
volts.
caught on to that point of view is because he never talked about a resistive layer, and you never
Well, he
mentioned
didn't
it.
have a resistant flux. But
If
Leah
you
did have it.
it,
Leah had it. Leah had it.
Oh.
Leah had it, and he didn't.
You refer to your remarks to Leo's.
Mine refers to Leah's result. I said, in Leah's successful run, he had 2 volts of overvoltage. And they were not present in your result. Maybe I didn't make that clear. But that was the point. You couldn't take over his results to Leah's results because Leah had 2 volts of overvoltage. He did not have. I think he understood it because.
This is quite different.
Yeah, I'm sorry.
Okay. Well, so what do we have? We have a positive voltage here. This is now not in relationship to your remark, right? This is just for my own thinking here. Let us suppose we do have some kind of
Flat
film
A,
all right?
iron
An iron conductor layer. Well, of course, this layer, who has proven it at this point?
Nobody.
Who knows anything about this property?
We know 2 things. We know the electrical characteristics, and we know that the silicon, aluminum, he had a sort of a cauliflower structure, and had aluminum, silicon.
Which might have precipitated out there or something.
I don't know how it
Some
got
kind of a layer.
But, well, we know 3 things. It probably was oxidized because it sometimes, before it settled down to this behavior, the voltage went up to 3.5 volts. And he had collected a support rod of iron, aluminum wire, very small, tying on it. he had not had some sort of an oxide layer protecting those, they would have electro-etched away and the sample would have fallen off. And it didn't fall off, so I assumed that these materials were oxidized.
But you have some oxidized layer on the
Right.
So then it depends very much on the properties of the layer. If it is four holes, for example, porous as many of these layers are, then it melts, still has access, and maybe flows in many regions of the electrode. So
Then he has very high current density in those areas. Who knows what it is? I don't know. I don't know.
yeah.
I've not been able to
So
make that.
I look mostly at what the Japanese guy told us today, and I found his talk to give me final answers to many questions I have had in my own mind and that I asked from Leo and never got satisfactory answers to.
Well,
And this Japanese fellow here today presented for me the first satisfactory insight that confirms in my mind many of the things that I had suspected would happen in this system.
well, absolutely, you will not
There he is.
get any significant overvoltage, and you get close to the thermodynamic equilibrium with 2 or 3 times, but fairly close to it.
Right.
Unless you have something funny going on like a layer.
So what his talk told me is that, as expected from the phase diagram, very low loadings.
The Japanese definitely had very low load.
Very low loadings. Leo never gave me any insight what his loadings would be.
Well, he does give the voltage of his electrolysis.
Yeah, but
You've got to plot it.
calculate from that to try to calculate the loading is far too hard. And assumptions.
Yes, well, he's not really specified because he recognizes it.
No.
It's on his problem.
Mhm. Yeah.
I can follow you, so I thought I feel my 2 glasses of red wine. I don't know how much.
I think, you see, I'm very,
One white, one red.
see, I have not been able to duplicate his behavior.
And you are doing
I
experiments
have done some experiments, yes, but I'm not really.
in your own private laboratory.
Well, NRF things.
Oh, wait, NIL.
In a very cold, not too oxygen-free recirculating box. So, I mean, the conditions are not particularly good. I haven't been able to get his electrical behavior, and therefore I haven't been able to check. The other thing is the anodes that I have run, which are ingots that are tied onto support rods, which is what he does, almost basically universally have not stayed together. They've swelled, they've fissured, sometimes they've powdered and disappeared entirely. And so I just haven't made a lot of progress. Now my next thing I'm going to try is to try anodes. I've gotten some that are iron implanted with aluminum. Maybe they will, we don't know how it got to the surface, but we do know the composition was there. Maybe these will work in the same way, and maybe the surface will be under compression and avoid this cracking stuff. I don't know. But if that doesn't show any progress, I don't quite know where to go.
But what is the cathodic reaction? Did you get any insight into that?
The cathodic reaction, yes, is just lithium. This causing electron going to lithium, but it dissolves into the aluminum into
Because penguins don't usually survive. That's what I
Jay, you gotta look. See? He's panning.
You really try it, don't you? You go to some really exotic places. Yeah,
And he can zoom and make you look even more risky.
We are still, but
was it last week?
we only don't know. The only one that
often wondered why electrochemistry is.
Did you also go to
Various other institutions, but not every
yes,
campus. They're just
when you climb right to the very top?
Even
Study crud.
What's that called?
Study junk. Study battery.
And once you get into it, I guess you're admittedly interesting. You tend to stay with it because you get into
Well,
into the cold fusion.
No, into electrochemistry.
Well, we were in corrosion. Corrosion is
Okay, that's it. Crud.
I was in charge of correcting corrosion in the nuclear power plant. And I had this project, you heard about the project at SRI that I had. I measured dissolved hydrogen gas in the primary site of a pressurized water reactor.
Hi, Tom.
Is used there to suppress
Hi, Tom Benson.
piping and radiolytic decomposition in the core. I'm just the staff. And in order to measure the dissolved hydrogen in the water, I decided, heck, let's put palladium wire, dip it in the water, let it spontaneously take up hydrogen, and we will measure the resistivity change. As an equilibrium, it's proportional to the amount of hydrogen that's in the water. And then I had this work going for 10 full years at SRI, who was an ex-student of Mark Fleischman.
Yeah, sure, I know.
I was opportunistic enough so that I wrote a memo on the same day that I heard the announcement to my colleagues who had money on this subject, innovative research money. And I said, I've offered my colleagues in my own department a chance to sign the memo with me. They all refused. And so I went, and now I'm here.
It's interesting you measure things. That's my background. I studied hydrogen insulated ICCF.
Some of this is up on the table.
He introduced me to you. I remember. Very
spent a lot of time in
So, for him. Yes. So,
She is to the organizer. And she is also to the hostess.
To Greek auditorium.
Here, the party givers.
This is my 15 seconds of fame.
Those are heavy water ice. Linda and Tom, you have done an absolutely superb job.
Yes.
This is all the work. I did all the fun.
Cheers.
That's right. Let's give credit where it's due.
Well, at one point she didn't think it was worth it. There about 2 weeks before this meeting. It's that low point just before the final thing.
it's when you got MS mail messages instead of, sort of real voicemail messages that you realize that things were getting
Well, I asked
At
her.
least you got to go to Hawaii,
I asked her a question that had already been answered some weeks before, and I realized it after I'd asked it on the phone, and I left a message. And so instead of calling me back, she put it on the electronic mail. Yeah. And furthermore, she sent it in the form of the letters that she'd already sent out. I asked her, for example, did they give time for the speaker's breakfast at 7 instead of 7:30? Because I didn't think I had enough time at 7:30. And instead of answering me directly, she sent me the letters that she sent to all the speakers.
Well, it's easy, just hit the button.
So I finally realized I pushed her too far.
I didn't realize you picked up on those subtleties.
Very subtle.
They wake up DOE, I say.
You can't wake up something that's brain dead.
They might have been able to do that yesterday.
What happened yesterday?
That was December 7th.
Oh,
Yeah. Yes, for us.
Anything short of that level.
Well, I don't think things are so hopelessly.
The Italians are doing good.
They're not so hopeless, Tal. They're just nearly hopeless.
Italians really came from
Yeah. Well, remember, they have the Enrico Fermi thing to follow.
That's right.
He was first with fishing. Now they're going to be among the first with fishing.
It's a matter of honor.
And they have Giuliano to remind them of that.
Would you like to hear a story about Giuliano?
Yes.
He was deeply offended by Rabinowitz's put down today, and so he wanted me to set up tomorrow's panel discussion with him and Mario on the stage to fight it out, to retrieve his honor. And so I proposed the following option that hopefully he finally accepted. I said, all right, we will now do a debate in print.
Right. Good.
And I will put it in the peer-reviewed package from this meeting with Mario's criticisms of what you've done and your response to it, and a couple of back and forths if you want, but basically the sort of thing that you would like to clear your name, and everybody would not be under the impression that you had made 3 major errors. Algebraic, conceptual, and what was the other one? I don't remember. Anyway, 3 major ones.
Stylistic.
So he accepted that, and I think that's a good way to resolve it, don't you?
Yeah.
Let the two of them on.
Sounds good.
And I sold that to him on the basis that I didn't think them being on the stage for 5 minutes would be anything but an ambiguous result.
That's right. Mario is very thorough.
Yeah, Mario is thorough, and so is, I think, I respect them both. They're both my friends, and I would like to see them, come back together again. But Mario, Preparata feels quite injured by the.
Didn't he get into the lawyer also somehow?
Well, yes.
Tom, that's the action of a diplomat.
I'm very proud of that. I found it acceptable. I've done that myself. That would have been a great thing to do.
When you have children,
I have never seen him in that strong a role, and it just goes to show that when the necessity comes along, they rise to it. Because all theoreticians are able to be very flexible.
whichever way the wind goes.
As Scott Chubb said to me one day, you bring any results you like, and my theory works.
Wait a minute, hold on.
Peter, I wish somebody took a photograph, or there is a video recording of you approaching Bush.
We have it.
And the fast retreat!
What was that all about?
Gentlemen, I am standing for him. Why?
Because he's a gentleman.
Yes.
What was this about Bush?
What is this?
Well, that's
Wait a minute, let me ask.
Everybody must stand.
Cheers, Peter!
Cheers.
Rico, and
I have to take the bottle.
Rico also. Rico for bringing us all together.
Absolutely. No, Tom Castle who brought us all together.
But don't expect me to drink now.
Our theory is so flexible.
That's good.
I can explain any result.
I forgot. You know all about
Except they have to relate to periodic order. I just love it when you told me about your hand-handling tutor.
1970. What's that? You work for Rumkin, yeah.
Don't say this right.
They joined the cult. They meant I was there for
Anyhow, we were talking.
Do you know some Russian? She speaks Russian very good. Do you know some Russian?
It's fascinating. Запоминали хорошие по Александру Сифурамкина. Хорошо?
What you have now?
Mr. Russian.
Especially.
To Tom Passel?
No, the Frumkin.
What is this now?
Frumkin in Russian.
Oh, Frumkin! Oh my God, I need 2 bottles!
You were trying to get the rice out of
Cheers to Frumkin!
There's the Frumkin.
How about I get a picture of Fitz holding that bottle?
Where is it? Here!
All right, Fritz. All right, Fritz, stay with it, man. Is there going to be a picture book organized in this conference?
Everything you take,
Just these pictures.
everything you take is going to be in the Wall Street proceedings.
Right.
Yeah, the Japanese had everyone on a stairway, right?
I'm in charge of the proceedings, so I'll put them all in.
This is an advanced Sony camera. It does direct translation into the Wall Street Journal database.
I'll have to tell the folks how hard a job it was here, and try to
We're
sell
all
that
gonna
idea
go
of
on
seeing
and
it's
mug
all
your row,
breaking
right?
Tom Passel, you want to get me fired forever, yeah,
You work for the same
This is my
place.
end game to everything. When I finally decide I'm going to leave, that's what I will do.
See, couldn't get in the front door doing cold fusion for every 3 went in the back door.
Now, Peter, you have to tell us what experimental inputs do you need in order to make your next theory?
You maybe
He
have
needs to know what's going to happen before it
you would
happens.
like fewer results, right?
Whatever comes, I mean, we aim to please.
I've heard that a mixture of mozzarella cheese and sour cream works as a new poison.
Published, by the way, all these reactions.
What I would like to know is why don't we get a reaction in ice?
Peter.
Encyclopedic
Oh, I'm sorry.
work that you did.
I think there should.
Oh, yeah. Oh, yeah.
Peter, I have to relate a story to you
What is this?
that is not meant personally at all. It has nothing to do with cold fusion even. But it has to do with theoreticians. But it has nothing to do with you
I
because
think that
you are beyond that kind of thing. Now here is a very short little story that happened recently. There is a beautiful effort at SRI International on a new concept of a zinc air cell battery, that is, right? Potent stuff maybe for an electric vehicle, who knows? And these guys came up in conjunction with an experimental professor at Berkeley, University of California in Berkeley, with a very nice, intriguing new concept. I'm not telling you any secrets, of course, I wouldn't do, right? That's information I can tell you. So these guys had this fabulous idea that they wanted to get zinc particles in contact with a carbon electrode, and the zinc particles are then supposed to dissolve, which they do, by the way, and then they had a gap behind that current collector where the solution was supposed to circulate all by itself. Okay? All by itself, meaning there obviously would be a driving force for the electrolyte to circulate. Now that would resolve this nasty problem, but you would need a pump in order to drive the electrolyte through hundreds of individual cells, all right? So anybody that comes up with a self-driven system where you wouldn't need a pump to circulate the electrolyte all by itself in each individual cell would obviously be a hero, right? So then SRI, in conjunction with this professor, Evans, in fact, Professor Evans at UC Berkeley, put in a proposal to DOE to get money for this very exciting project. Well, DOE then turned to the theoreticians at Berkeley and asked them, can this work? Well, the theoreticians didn't take too long.
You got the wrong theory.
Therefore, I said it has nothing to do with Peter. Now, wait for the close of this story, all right? The theoreticians came back to Berkeley and said, after like 2 months, and $100,000 down the drain.
They
said,
DOE,
DOE, they said, this can't possibly work. This is a whole lot of nonsense. Don't spend any money of it. Well, this story went back, of course, to Evans and SRI, and they said, this is ridiculous, you know. We have to show these fellows that it does work, and we will demonstrate it to them in a little demonstration device. So they invited DOE, those theoreticians, to the same place, and they made a demonstration device where they added some dye, and you could see the circulation of the electrolyte in this little cell. So they provided the proof to the pudding.
So what happens?
All right, now, the gist of the story is the theoreticians went back to their labs, grabbed their pencils again, and it took them another 2 months to come up with a new theory that predicted that, in fact, the electrolyte should circulate.
I have some cynicism.
I have a story, something like that, which is...
I'm sorry, that's a fact. There's no cynicism.
Bad theories.
I have a story also. It relates to cold fusion.
Oh!
Maybe I shouldn't tell it.
No, that's all right, Peter. Go ahead.
I got a visit a couple of weeks ago from a very senior funder at DOE. Maybe not so senior.
Anyway.
And she's reasonably new in her position.
No, not Krebs.
Mildred?
Not Krebs. And Walt Polanski suggested to her that I was a good guy at MIT and she should make an effort to stop by and talk to me. So I was very busy, but I made some time. I thought, a funder wants to actually come to me? I was scratching my head thinking, has that ever happened before, ever? No.
Did you write it up?
I mean, usually it works the other way.
Right. Fantastic.
So I thought, oh, this is great. Finally, DOE's finally starting to see the light. They're going to come and cheat me. This is going to get me into a whole lot of trouble.
Wrong attitude.
This must mean that you've turned coat on us. If DOE's coming to you for money.
No, not for money, but Polanski said that she should come up because he told her that I was a wise person up at MIT.
Well, you are.
And, well, I wish I were.
Wise guy.
Wise guy.
Wise guy. So she came up, and I showed her around our X-ray laser laboratory, and she was very impressed that we were still in business a year and a half after having our funding cut off.
It was called Life After Death.
Okay, then the topic turned to cold fusion.
Oh, God.
And she said, well, she didn't believe in cold fusion. I said, well, you know, these things happen. Are you interested in chatting about it for a while? And she said, sure, I'm open-minded. I thought,
That in itself is a rare event.
it is.
It shows she was new at DOE.
He was really new.
So what happened? Okay, well, here's what happened. I said, let's talk about this. She goes, well, what's going on in the field? I said, well, good things are going on in the field. The folks are seeing some excess heat. And she goes, well, how much excess heat? I said, well, various claims, but, you know, for example, Bonzo Fleischman are claiming in 10 minutes they're seeing equivalent of 200 electron volts per atom, you know, of cathode. And I said, you know, that's interesting. And she said, well, let me think about that. She said, you know, the folks, the company I keep, you know, we have a different opinion about that. And she said, on the one hand, cold fusion's not new. 2, well, it's 5 years old. It's no longer new. She goes, it doesn't work. There's no way to get the deuterons close together. But the third is that the energy measurements are either A, in error, or B, can be explained by surface rusting. Rusting of the surface.
Oh.
And I said, hold on. Let me repeat it. I said, these numbers are
200 EV per atom.
EV per atom. And that's for volume. For surface, it would have to be much larger. How can you explain that by surface rusting? That's no problem. I used to work in this field. In electrochemistry. She said, I did an experiment. She goes, it's really easy to be fooled by it. I loaded a palladium cathode up, or I don't know if you remember it's palladium, but I loaded up a cathode with hydrogen, and the thing exploded. And it took out part of my laboratory. Those things could be really violent. They produce a lot of energy. I said, if you took every single hydrogen atom or deuterium atom that was in and you burned it like jet fuel, you wouldn't come close to the amount of energy. She goes, no, you're mistaken. You don't know what you're talking about. This can be explained by rusting. I said, okay, let's start. How many electron volts in a joule? It became clear before it was over that she didn't understand what energy was.
What? And she's from the Department of Energy.
Peter, and when I realized that, I lost my enthusiasm for trying to convince her.
Get funding.
That's enough. Her she needed.
She didn't know the difference between energy and power, or just didn't know energy. Period.
She could not. She did not apparently realize the significance of a number of 200 electron volts per atom not being accounted for by surface rusting.
Or by any chemical phenomenon.
I mean,
what was her background?
Oh.
Her background was kissing lots of congressmen.
Well, that's enough
the thing
for
is,
me to vote for Peter Higgleston for president.
I don't know. I got very discouraged about it, and I basically gave up at that point, thinking that I was going to be able to convince DOE funders about.
Well, you might as well be realistic.
Dave Nagel.
You might as well be realistic.
Dave Nagel's not DOE.
I know. DOE.
Well, have you ever thought about us finding one of us to infiltrate DOE? They are always having, new staff on board. After all, this lady was new. Every now and then somebody dies and they have to replace them, I suppose. Not from our ranks.
Well, let's see.
Crandall, wasn't it?
After
Crandall, I think.
After 30 years, INL's out now. So
that's right.
Turnover rate, if it's 25 or 30 years.
Here we go. This is the long-term we're dealing with.
If we've got this moment for another 20 years or so, this is...
But Peter,
always has to
you try to set her straight. You try to set her straight, I suppose.
I sat there, and we went through, I went from beginning, I said, now this is how many electron volts per atom, this is how many in the volume, this is how much on the surface, this is how much energy is involved for the loading, this is how much energy is involved for combustion, and so forth. And she told me that I didn't know what the hell I was talking about.
She still told you that? After that?
Yeah, not only that, the further this went on, the more that she kind of like insinuated that me and fellow co-believers, were big on belief but not big on
Did you
thinking.
part in that vein?
No, what happened is I recognized that this was a battle that I could not win. And so I relaxed back, I looked at my watch, I thought, I have work to do, and I tried to be polite and inquired if she needed help to her car, and I walked her to her car and we talked. And she explained to me a number of things. She said that DOE policies changed now. That DOE had to focus much more now on energy issues.
I can't believe it.
For example, it's like 1984.
Really?
Okay, so she said, we went on it, and she said that she was sorry that DOE couldn't continue funding in the X-ray laser end of things, but that basic energy sciences was reorienting towards energy. She said, well, look, here, I'll show you the list of new projects and so forth so you can see for yourself. So I flipped through it, and here was some femtosecond optics, and here was some synchrotron studies, and here was some high-speed electronics research. And I flipped through and I said, well, yes, I can see this really is very much more energy-related than it was before. And at the end, I told her, I said, well, I apologize. I said, I would like to apologize for my behavior. It's kind of frustrating because we've worked for many years building up this X-ray laser and working on this cold fusion. We can't change due to the wiles of the change of the funding patterns overnight. And I said that it's just frustration. Maybe you meet other people who are frustrated with the funding policies. She says, yeah, we know. We meet people like you.
I bet they do.
So,
People who understand the difference between.
That's absolutely frightening.
You like my story?
No. Did she replace Dwayne Barney? Did you know Dwayne Barney?
Yeah, I knew Dwayne Barney. I
Because
think
she
she
was
is the
about
replacement.
to retire.
That's right, Cynthia Carter.
Well, it's not unusual at all.
Which school did she go to?
Oh my God! I mean, I think that doesn't know that. I mean,
I didn't get
convert
it
her.
wrong.
You guys are thinking wrong. We have to convert her.
He said it's loaded.
I think we have to
so
convert Al
optimist.
Gore.
He said I have
If
to.
you can
No,
find
you
them,
can't.
convert them.
Right.
You can't convert.
Peter, why don't you go there and give
Why do
them a
you think
lecture
that?
on
Because
what
I know
an
people who
EV
tried.
is?
No, actually,
You know,
I think we have to convert
It was
John.
unfortunate because the more that I tried to explain it,
Sad
what the issue was,
Hazenga's
the more
almost
she
impossible.
No,
bristled
Well,
up.
he said
he felt
after I said how do you
insulted.
explain 200
and-
rules, 200
Well, who
EVs
is the
per
person,
atom?
you know? It's
He
like,
said it's all
is-
But
storage.
honestly, which university
He's
did
too
she get her
the
degree
person,
from?
not John.
Hazenga's smarter
I
than
haven't,
that.
I haven't
He is,
followed
John
it.
Huizenga does.
I'm
know
very
about it.
discouraged. I don't think there's any, I mean, if you've got somebody from the Department of Energy who you can't make an energy argument with and have her understand
I
it,
really do think Dave Nagel is the one.
I mean,
There's only one person.
Yeah.
It's
But to
silly
tell
to
you the
think
truth,
I do
I
think
know
Dave
Dwayne
Nagel would
Barley
be
from
good.
the old
I know
days
Dwayne Barley.
at General Electric, right? I have known Dwayne for 20 years or so. If you would ask him, tell me what the energy equivalent in kilocalories
You
or
like
kilojoules is for one EV, I don't think he would be able to tell you.
Swinger.
Yeah, you have to put it
Honestly.
in all kinds of different units.
So you
for-
honestly, you have to help them. You have to. I really mean
But
that. You
can-
have
can
to help
somebody-
them and educate them.
You
with a
were
lot
in
of
the
patience.
Jasons.
hold on a second.
Wait a
That's the right attitude right
There's
there.
no question.
You're right.
Can
You
somebody,
have got to.
hold on a second. Can somebody explain to me how folks in charge of funding in the Department of Energy cannot know what energy is?
Yeah, he's
They
not
know
talking
about
about.
Al, right?
That was a surprise to you?
They don't pay, Peter, they're ignoring what you say. But you were part of the Jasons, right?
Yeah, the Jasons are good.
But they wear hats or whatever.
Who on the Jasons do you think could be convinced?
Dick Garland.
Well, I heard that.
No,
Really? You
no.
think so?
He's,
No,
he's the only one that I have.
What about
for.
Freeman Dyson? Is he
I
on the
thought-
Jasons?
Is he a Jason?
Dyson dead?
No, he's not dead. He's very much alive.
He's alive. He's dead.
Dyson was the one who brought peace to Schwinger and Feynman and all these guys.
No, I understand that. No, Dyson is
he
beyond.
No.
No. Dyson doesn't have the patience to deal
So
with
you
any
really
of this
think
full-on-
Dick Garwin is
Dick
the one?
Garwin's the only one.
Okay, well, he's the
He
one.
came to the SRI for
Yeah,
a whole day.
which is- Which is
Right.
very good.
And
Lee
he-
Hammerstrom did that.
And he went
Yeah,
back
no,
and said it was all a
Yes.
bunch of bunk, right?
He
He's
worked
the one who
for him.
funded me for a year. Lee's a good
But
guy.
Dick
I heard that
Garwin
he,
is very good.
couldn't find anything wrong, but they still didn't endorse us quite, but they didn't knock us.
So maybe he's the one to be worked on.
It's not worked on. You don't work on Dick Garwin. Dick Garwin is a highly
No, Lee
intelligent
Hammerstrom.
fellow. Oh,
So
I
he's,
found
if he's so damn intelligent, why doesn't he believe it right now?
There's
What?
a difference
He's a
between
good guy.
being intelligent and being informed.
Dave
Yeah.
and
He's
Lee
very
know each
So
intelligent.
other.
why is he informed? Did he read your paper on the Nagoya conference?
Lee
I don't think he's
Lee-
read anything that I've read.
Lee
Is
is
he
Mike
saying the
Well, then he's
Canadian
not
Broadcasting
intelligent.
Video?
Lee is Mike
Is he saying the
Newman's
Canadian
boss.
Broadcasting
I don't-
Video
I
for
don't-
starters?
Strong.
Lee
Okay,
is
so what should I
very
work on
open-minded.
Sounds like it.
What should I try next year?
Do you know?
I've never been in.
I
No, I
conversed
think
with him over the
Paul-
phone.
I think.
Garwin.
Yes.
So that I have to pick very carefully what I will be saying this morning because of lack of time. I want to start first with some equilibrium considerations. There's an empirical relationship that's called Siebert's law, which simply that concentration at low concentrations in a metal of hydrogen or deuterium, we find that that's proportional to half power of pressure. That's consistent with this kind of chemical equilibrium that the molecule associates. So therefore, from this we know that at least at very low concentrations, the hydrogen and deuterium in the solid is in fact associated. Now, what happens is that it occupies the interstitial position. We know that because of the fact that partial molar volume is a positive quantity, the lattice parameter increases. I'd like to show you, in connection with something else that we should discuss, how to visualize what happens in the lattice. And follow a simple model that simulates, from the density energy, the elasticity point of view, what happens. When you introduce in a cavity in a solid, which is cavity being too small for what you wish to introduce, a larger ball, a conceptual experiment, a kinetic experiment, introduce that large sphere into the too small cavity, the cavity must expand. In the process, the wall of the cavity sweeps out a body, which I will call V1. What you find is that the external surface of the entire body sweeps out an even larger volume, V2. V2 is related to V1 by Poisson ratio, and in case of Poisson ratio of about 0.3 or about 1/3, you find that V2 is about 1.5 times larger than V1. This is the origin of the fact that the partial wall volume is a positive quantity, and the fact that the lattice parameter, delta A, is a positive quantity. The external surface of the body sweeps out a larger volume because of the distortion produced in the center of this center of dilation. That is actually produced inside. So in fact, as you increase the number of interstitial solids in the solid, you find that the lattice parameter increases, more and more room is made available for the successive insertion of solutes. Now that will become important for a while. I wish to call your attention to a few facts which may or may not be important. By the way, I should have said that I'm following the philosophy of Bob Huggins expressed yesterday, namely that in topics such as cold fusion with such great difficulty in the reproducing of experiments exists. We must pay attention to many details. And right now, we don't know what is important, so I'll take it upon myself to look at the whole field as far as I can, because we don't know about what in fact be very important to understand later on. The sodium, hydrogen, as well as carbon, nitrogen, and many metals force in interstitially, so it's important to know something about those interstitial sites. In the FCC lattice, there is one octahedral position per mineral atom, but two tetrahedral positions. In the BCC, there are 3 octahedral types and 6 related tetrahedral types. The underlining means that, in fact, that is the larger cavity. In the FCC, the octahedral is a larger cavity of the 2 types. In the BCC, it's a tetrahedral. But don't think for a moment that the interstitial solute likes to occupy the larger site. That is, in fact, the case of the octahedral site in FCC palladium. That's not the case in BCC iron, for example, with the carbon, and presumably also the hydrogen occupies the smaller, the octahedral site. Now, there's a distinction to be made between a substitutional solid solution and an interstitial solid solution, which is rather important. When you add a solute to a solvent, and the solute occupies a lattice point, we call that a substitutional solid solution. As you add the solute, you also increase the number of lattice sites for the atoms. That's not the case for the interstitial. What you're doing is simply filling up already existing finite number of positions. What that does is that it forces one to use Fermi-Dirac statistics to express the chemical potential of the dissolved species. At equilibrium, therefore, you will have 1/2 the chemical potential of the hydrogen molecule equaling the chemical potential of the dissolved species, and you must express, in the general case, the activity, the amount of activity of the dissolved species in this form. Gamma is the activity coefficient, theta is the degree of filling of the lowest energy category of interstitial sites of finite population. The consequence of this is that as one increases the population in that category of interstitial sites, what I would call category 1, the lowest energy, which is the case of FCC palladium, which is the octahedral sites, as that approaches unity, the activity necessarily goes to infinity. So therefore, that means if you cannot apply sufficient external chemical potential of the gas to fill all those interstitial sites, in case of hydrogen, the palladium, and the octahedral, what has to happen is it spill over into the next category, the higher energy category, which is tetrahedral in that particular case. So you cannot have full completion of the lowest energy category, and this is something to keep in mind, especially if there are theories of cold fusion that depend in some way upon a perfect distribution or near perfect distribution of solutes in the lattice. In addition, one might say that because the tetrahedral sites in palladium represent a higher energy level, that means also that the diffusion among nucleosides would probably be faster. They already are a higher energy state. Let me go on now to interaction of solutes with imperfections, structural imperfections. We spoke about how we spoke of dislocations yesterday. There are two extremal types of dislocations. The ace dislocation, which I'll visualize here in a very simple diagram. Effectively, an ace dislocation is simply the locus of the termination of an additional lattice plane. So here we have n plus 1, here we have only n in the same linear dimension. This region is a region of latency, as well as pointed out yesterday, and that is where solutes interstitial type like to gather. One cannot express their gathering here, excess concentration here by elasticity theory. One can do it far away, but at the core, it is one can do that only with unprovable assumptions as to what's going on here. So one usually has to make a measurement. In the case of hydrogen and palladium, well, by the way, when I use the word hydrogen on that otherwise specified, I mean either protein, deuterium, or tritium. We'll make distinctions as they are necessary to be made. The interaction is about a negative 60 to 70 kilojoules per mole of H. So these you might call one-dimensional imperfections. There are two-dimensional imperfections in solids, all kinds of interfaces, both external surface as well as internal surfaces, between phases, for example. And grain boundary is also another type of two-dimensional interface. And there are well-known interactions. In the case of palladium with hydrogen, the interaction is about 5.3 kilojoules per mole on the average, with a Gaussian distribution of about 15 kilojoules per mole. You can see from this that therefore there are also some repulsive interactions as well as the type of interactions at grain boundary. A vacancy, rather amazing to me, a vacancy in palladium is the highest interaction energy with dissolved hydrogen. This is an inference, as I mentioned yesterday in the discussion, made from measurements by Kirchheim of the partial molar volume. When one introduces an extremely small fraction of ppm of hydrogen in palladium, he found that the partial molar volume is a negative quantity. The thing shrinks instead of expanding. The only way to understand this is that in fact the hydrogen entering or the adjacent to a vacancy. And we already see a large interaction energy with dislocations, but by virtue of the fact that the first bit of hydrogen that is injected goes into must go into an even deeper trap, and we see a negative partial molar volume. That means, therefore, that the interaction energy must be larger than this, and I yesterday gave an offhand estimate of about 100 kilojoules. Okay, that's what this says. In addition to interaction with structural imperfections, dissolved hydrogen also interacts attractively and sometimes repulsively with chemical imperfections, which is to say impurities. Now, I'd like to give you some understanding or some insight into the effect of mechanical stresses. If you want to compare equal concentrations of dissolved interstitial solutes, of which hydrogen are a prime example today, at the same concentration between a solid which is under mechanical stresses and one which is completely relaxed, no mechanical stresses, the difference in chemical potential of the dissolved species, or the interstitial is given by this expression, is sum of many terms, of which we have Vm is the molar volume of the solution as a whole, Sij are the elastic compliances, X is the composition, the mole fraction, as to say, of the solute. Sigma is the stress. Actually, we have to worry about the entire stress tensor here. The convention, by the way, is that sigma or stress is a positive quantity when it's tensile. In the case of the square of the stress, whether it's internally generated or externally applied, if that ratio over Young's modulus is a small quantity, and in case of isotropy, this complex equation can be reduced to the simple form where we have the partial molar volume of the interstitial solute times the trace of the stress tensor, which we call, 1/3 of that we call the hydrostatic component of stress. This can be converted to give an expression for the excess concentration in tensile stress field for constant chemical potential between the relaxed body and the stressed body. This is a perfectly general thing. This is a simplified version of this. And if you look at this carefully, you find that the shear stresses also play a role, a lesser role than they have to have performance stress, but not zero. So that in the field of the spinal dislocation, you will have also an enhancement. Suppose you have grown a beta phase palladium, for example, beta palladium, inside of the alpha phase. By virtue of the fact that the palladium atom is effectively immobile compared to the mobility of the dissolved species hydrogen, the beta phase will initially grow in such a way that only hydrogens will accumulate the higher concentration in beta, leaving the lattice lines between the alpha phase and the beta phase effectively continuous. We call that a coherent precipitation or coherent growth. The consequence of that is that because the beta has a larger, in the beta phase, the partial molar volume of the hydrogen, although it's somewhat smaller, there's more hydrogen here than in here. This is a larger volume than the cavity which gave rise to it. As a result, this really exemplifies that elastic model that I showed you earlier, and one has effectively a compressive force upon the beta. And out here, to a first approximation, this is spherical, one has zero hydrostatic component of stress. So that its concentration is therefore increased. In that situation, now I'll make one more reduction. Not for the case of beta phase palladium, because that's really a solid solution, but rather if this were a stoichiometric hydride, such as TiH2, which has a very narrow range of composition, then one can express the spatial variation of concentration of hydrogen in the matrix out here by this sort of expression. The overall concentration at infinity, which is to say far away from the disturbance, the elastic disturbance over here, is raised by the fact that there is hydrostatic pressure upon beta. But there's also a spatial variation, which is given by this expression. Whenever you have an inhomogeneous stress situation in the body, you will have an inhomogeneous concentration distribution in the body at equilibrium, by constant chemical potential everywhere in the system. In the case of something like the beta phase of palladium growing inside of the alpha phase, this sort of equation is not sufficiently complicated. It is much more complicated equation that developed. But in that case, you have a similar thing. You will have an enhancement concentration out here and a spatial variation. This considers give rise to two kinds of phase diagrams in systems such as mental hydrogen system, the coherent and the incoherent phase diagrams. The coherent phase diagram results in a truly thermodynamic equilibrium between one phase and the other. They are sharing the solute at the same chemical potential equilibrium, but by virtue of the stresses, the mutual distribution between the alpha and beta phase is different from what happens when the beta phase breaks away from coherency by nucleation dislocations that interface and emission of those dislocations, the great boundaries on the external surface. That develops a different concentration distribution, therefore a different phase diagram. The coherent phase diagram is really thermodynamic, but it's a metastable, a higher energy, higher free energy situation. To go from coherency to incoherency, one has to have nucleation dislocations, which can happen only when the beta has grown sufficiently large so as to be able to pay for the energy creation of dislocations by the energy diminution of going from coherency to incoherency. And this is the basic reason why when you try to establish a phase diagram in mental hydrogen systems, you have hysteresis. Because in no case do you have perfect coherence or perfect incoherence. You always have a residual dislocation distribution and therefore a higher free energy situation. Because of the interest shown yesterday, I published a talk about what happens around dislocation. One can calculate the stress distribution about dislocation, therefore the chemical potential, the concentration of hydrogen at a constant chemical potential everywhere around this location. It's an edgeless location. We have a dilating field on the lower side. The missing line of atoms is on this side. Here we have a compressor field. These are isoconcentration lines. Here we have a ratio of 50 between the original stress-free concentration and the existing concentration of the stress field. And you see how this goes. These, the radii are given in terms of elastic parameters. G is the shear modulus, B is the Berger spectral dislocation, nu is the Poisson ratio, B bar is the partial volume of hydrogen. I don't want to take much time with that. Let's go on to some kinetic consideration for hydrogen in metals. In general, we have a diffusive flux J, which is motivated by the gradient chemical potential. B is the mobility, C is the concentration. We can expand this to bring in the two important terms that contribute to the free energy, namely the concentration gradient times a thermodynamic term, which is the variation of the logarithm of the activity coefficient with the concentration. This can be very, very important. Here we have a contribution from the stress state written in simplified form, forgetting about everything except the hydrostatic component of stress. Partial volume of the interstitial species. So that can be written in this fashion, where now I combine the mobility with the Einstein relationship to form the diffusivity. And that already includes the thermodynamic term. Now actually, this is not a minor component in the process, or ingredient in the process, because you can, at equilibrium, say at temperature 295 Kelvin, you find that it takes a stress gradient, or difference, as you say, between one point and the other, between those 2 points, there being a delta C, a concentration equal to C minus 0. That delta C can be counterbalanced by a delta of the hydrostatic component of stress of this magnitude, 1.5 10th dyne per square centimeter, and no diffusion will occur. So it's a major contribution. The force that is motivating the flux under stress gradient can be expressed this way for these conditions. In addition, one more thing I want to say, that people have measured the ratio of diffusivity of concentration in highly concentrated hydrogen metal solutions. And one finds that there are regions of the phase diagram where D goes essentially to 0. Now the reason for that is that this term goes essentially to 0 in the neighborhood of the critical temperature of composition. That's a well-known retardation effect. Mobility does not go to 0, but the overall diffusivity does. That's because this thermodynamic term. There are other reasons for fluxing, for diffusion, and I will say only a very few words about this because this came up in one of our discussions earlier on this week. One can have a gradient of electrostatic potential, one can have a gradient of temperature. I will say nothing about this. These are very, very complicated phenomena and very difficult to understand. If one has a gradient of electrical potential in a system, there's a force that can be expressed this way by something which we call a Z star, effective charge in units of electron charge. The flux, the diffusive flux, is given by this expression. Never mind this, what I just want to point out is that if you want to induce electromigration in a metal, you must of course apply electric field to the metal, and you necessarily incur a large flux of electrons and electron holes, depending on the nature of the metal. The species that's dissolved in there is a tightly screened proton, in the case of hydrogen metal, screened by free electrons. And by the way, introduction of the hydrogen into a metal modifies also the bands, the energy bands of the metal, so we have not only local but also extensive long-range interactions. But what I can say is that when you establish the magnitude of the Z star, you find that hydrogen radium has a positive, something like 0.6. You must not infer from that the ionicity of the hydrogen dissolved is 0.6, because what's happening is that this thing responds not only to the electron, but also to momentum transfer between the flux of electron holes, one direction, the other direction, and the dissolved species in its activated state as it's jumping from place to place. I don't want to say more about that because I lack of time. Now I wish to discuss the problem of effective fugacity, which has made problems for some of us in the past. The fugacity is a gas-based dynamic property which comes about from one's desire to express the change of Gibbs-free energy in terms of other parameters that have hydrostatic pressure and temperature, SE entropy over here. If we carry out a process at constant temperature, the change in Gibbs-free energy is given by a simple expression, which for an ideal gas, using P is equal RT, becomes this. In order to have the same formalism for a non-ideal gas, in which hydrogen at high pressure is, then people have used this formulation where now F is called fugacity. So that's a very general expression. Fugacity, therefore, its changes are the measure of the work at constant temperature that gas can do. The chemical potential of the hydrogen molecule gas phase is therefore given with respect to a reference state by this expression of ratio divided with the ratio of fugacity in the existing situation divided by the fugacity of the standard reference state. Therefore, one will express the driving force for entry, not kinetics, just the driving force for entry between the gas phase and the solid solution of hydrogen in the solid electrolytic expression. The difference between those two chemical temperatures expressed this way. Perfectly, in general, this must be expressed by the fluid acceptance expression. At equilibrium, therefore, one has that the concentration is a function of fugacity of the gas phase. Concentration of the solid function of the gas phase. And therefore, what I call C0, namely the subsurface concentration just below the input surface of the solid, which controls the subsequent diffusion further into the solid in non-equilibrium situation. That C0 is also a function of fugacity. Now, of course, the kinetics of entry of going through the interface must be considered in the overall transport process. But if you have diffusion control, not kinetic control, for the ingress between the adsorbed layer and the subsurface layer, then you can say that that subsurface concentration is in fact a function of fugacity, and because fugacity is completely determined by the hydrostatic pressure at any one temperature, it's also a function of the external hydrogen gas pressure. Let's go on now to charging from other than molecular gas. Consider here two cases and one figure. The case of charging of a partially dissociated gas, say when you have a hot tungsten wire in a low pressure gas phase, you generate hydrogen atoms, hydrogen ions. They are bombarding the surface, and they form some kind of adsorbed layer, and then that generates a C0 inside here. You cannot describe the driving force between this phase and the solid phase in any thermodynamic terms, because in the case of the partially dissociated gas, we don't have thermal equilibrium out here. In the case of the cathodic charging, the adsorbed population is controlled by competitive kinetics. However, we like to define what we call an input fugacity or effective fugacity, such that the C0 that controls the subsequent diffusion inwards is in fact a function of that input fugacity. And we will say that the input fugacity would be the same as the fugacity in the gas in molecular gas charging, which gives the same C0 in here. Now that input fugacity is a totally kinetic quantity, cannot be calculated in thermodynamics, and it is not associated with the hydrostatic pressure. As I indicated before, when you ingress or you input hydrogen into the metal, the lattice expands, the outer surface goes out farther than the internal surface around it.